Hi everyone, I hope you all are doing fine. You just saw a demo of a 8-bit random number generator. And I just wanted to start with the small demo because anytime you see the final product, it just makes things a lot more easier to understand, right? So we're going to start off with a block diagram for the random number generator, and then we're going to move on to the functional block diagram for the entire project, and then we're going to start coding. Imagine you have 8 D flip-flops, and I label them as D7, D6, D5, D4, and so on. These are the 8 data lines that are being fed into, that are going to be the data lines for these flip-flops. These flip-flops are positive edge triggered, and they're connected to a clock. We also have a reset, which is going to play an essential role, which you will see later on. The output of the individual flip-flop is becoming the input of the following flip-flop. For example, Q7, which is the output of flip-flop, becomes the input D6 to the following flip-flop, and so on, right? Also, notice here it is important to realize that Q7 here is a most significant bit, whereas Q0 is the least significant bit. Another thing that's very important, because it's going to be an 8-bit random number generator, a true random number generator is which does not repeat the number in a sequence, because we have 8 bits, so there are 255 different outcomes. Now, if a number is repeated before these 255 outcomes, different numbers have been generated. If your number is repeated after say 7 outcomes or 8 counts, it's not necessarily a true random number. So therefore, we need to make sure that what are those step locations, which basically ensures that the number is not repeated unless it has gone through all 255 outcomes. So according to the Xilinx online documentation, step locations for 8-bit LFSR is the 8th, 6th, 5th, and 4th bit, which is an exclusive NOR. So what I did here, I took the 8th bit of this random number generator, which is Q7, 6th, 5th, and 4th, which is Q5, Q4, and Q3. I fed them into exclusive NOR gate, and the output always goes into the first D flip-flop from the left, which is basically, it becomes the D7. This is what goes in. Now, imagine the current state when we reset the button, when the reset is pressed, then essentially everything will just become 0. So the most significant bit is 0, Q6 is 0, Q5, everything is 0, right? Which means the output, the actually input to the exclusive NOR gate is all 0, because Q7, Q5, Q4, Q3 all are 0, which means the output to the exclusive NOR gate is going to be 1. And that 1 is fed into D7. Now when the positive edge of the clock arrived, all these D flip-flops are synchronously triggered because it's a synchronous clock. That is going to mean there is going to be a shift in the logic. So the one that you see at input D is going to move to the right. And therefore the sequence will look something like this. You have Q7 1, Q6 0, everything that you see in green, right? And if you look at the binary sequence, it makes a sequence of 1 0 0 0 0 0 0, which is equivalent to 128D, which means that the first number, random number that is going to be generated, it's going to be 128. And you saw that in the demo that the first number that you see on the screen was 128. Now if you look at the logic for Q7, Q5, Q4, and Q3, that has changed, right? Q7 is 1, everything else is 0, and that would mean the output of the exclusive NOR will be 0. This 0 is fed into D7 again. When the clock arrives, it's going to shift the logic to the right one more time. So your new random number will be 0 1 0 0 0 0, and that would make a decimal representation of 64, a binary representation of 64, right? So this is essentially how the random number generator is working, all we need is 8 D flip-flops and a combinational circuit, which is basically exclusive NORing, output Q7, Q5, Q4, Q3, and is fed into D7. And finally, I'm going to have another input to these flip-flops, which will be load. Anytime this is going to be a push button on my Basys 3 board, anytime a load button is pressed, whatever is the logic at Q7, Q6, all the outputs of these D flip-flops will be displayed on the 7th segment. I also want to quickly go over the functional block diagram for this project. We have a debounce button. The reason I have a debounce button is because I wanted to make sure when I hit the load button, this is basically a button right here, which is a load button. And I wanted to make sure that I don't skip on any of these random number. So I have a debounce button, and it is basically loaded into individual flip-flops. So there are a total of 8 D flip-flops. They are vertically stacked on top of each other. The button is the load button, which is basically coming off the debounce, the output of the debounce button. You have the input D in each of the flip-flops. You also have a reset and clock, and you have the Q, which is then fed into the binary to BCD module. Also, if you notice over here, Q7 was being the output Q7, Q5, Q4, and Q3, those were being fed into exclusive NOR gate, and they were becoming input to D7, and that's how it is over here as well. You have 7 and 5 exclusive ORing, then you have exclusive ORing with 4, then exclusive ORing with 3, and then you have a NOT here that is making an exclusive NOR gate, and it's fed into D7 right here. So you got D7, D6, D5, D4, D3, all the way to D0. Everything else that you see over here, including slow clock here as well, is part of the binary to BCD video that I've done in the past. So I'm not going to go over it in much of detail, but this is the most important part right here in the middle that we're going to focus on. So I want to start off with the D flip-flop, how the Verilog code would look like for D flip. It's pretty simple. I've done it in the past many times. I'll go it one more time. As you can see, I was showing the block diagram of D flip-flop. We have the clock reset, we have the load button, we have the input D, and then we have the output Q. The reason output Q is declared as register because it's acting as a memory, so it's going to be able to hold the logic. Every time positive edge of the clock arrives, we start off by saying begin. If the reset is high, if the reset pin is high, then we want Q to get to 0. Else, if that's not the case and load is high, means if this statement is true, if the load button is high, only then D, which is the input, it propagates to Q, to the output. And again, not to forget, remember folks, what is the next state logic for D flip-flop? It's basically pretty simple, that your key Q, which is the output, is always equals to D whenever the clock is high, So that's pretty much, that's pretty simple right here. I also have a debounce button here. I don't want to go into much detail here because I have done a video on it separately, and everything else that you see over here is again part of the video that I was mentioning, and I'll leave a link in the description as well. But I want to take you to the top module because that is where everything exists. So the way it's working, I have the input clock. This is the Basys 3 board clock. This is the, remember, this is the 100 Hertz clock right here. Then you have the input load button. This is to generate a random number generator and then display it on the board on the 7 segments. We have a reset button, and then of course we got the seg and end. These are the segments and the enablers, right? Just simply creating a parameter 0 here, assigning it a value of 0000, there are 255 random numbers will be generated, so therefore we only require only 3 segments since it's an 8-bit counter. So 255 random number will be generated, so we require only 3 segments. The leftmost is always we just want to keep it it's just simply going to be 0. We're not going to actually activate the leftmost segment because Basys 3 board has 4 7 segment on the board. Everything that comes out of the individual modules that you see over here on the left, this right here, everything over here needs to be declared as a wire. And so this is what I did here. This is my slow clock, the 100 Hz clock to toggle the 7 segments. This is my mux, my counter out, my ones, tens, and hundreds right here. Okay, then I have the debounce button. The debounce button is for generating a new random number to make sure we don't skip a number, right? So this has also been explained in the video. The link is over here. I will leave the link in the description as well. And I just declared that debounce button as a wire, and this is a module that I instantiated to, you know, get the debounce to work. Now a little bit of theory. Again, I already mentioned little stuff about LFSR. This is basically the block diagram of the D flip-flop that I was showing you. It was essentially an LFSR that we are implementing, and the width of the LFSR, which in our case it's 8 bits, and its repeatability, like you don't want to repeat any random number. These are the things that must be kept under consideration. There is a connection between LFSR width and its repeatability of any number being generated. So an n-bit LFSR will be able to generate to the power n minus 1 random bit before it starts repeating. So for example, if you have an 8-bit LFSR, which we have, it will generate 255 random states before repeating. So for most practical purposes, this can be considered as a true random number. In LFSR, the most significant bit will always be the feedback point. So you saw that over here, the most significant bit, which is Q7, the output is being fed into D7. So this is always going to be the case. You then have coding an LFSR. It is important to know which bits are taps to be selected for exclusive NOR gate. Now know that because we were doing what do you call it, a 8-bit, so these were the taps that we chose. If you are going to use a 7-bit LFSR, then these tap numbers will change. You need to look at this documentation right here. Again, I'll leave the link in the description. If you're doing 12-bit, these numbers will change, and these numbers are critical to be able to not able to repeat any number before you run out of all the possible sequence or outcomes. This could be confusing as the taps are different for different size register. I just mentioned that. For example, 8-bit LFSR will have its 8, 6, 5th, 4th bits exclusive NORed with each other. In some cases, it can also be exclusive ORed. I went with exclusive ORed gate. Xilinx has online documentation, and the table shows, there's a table in the documentation where you can find all this information, and they cover bit size up to 168 bits. Now let's come to the meat of my Verilog code here. This is the meat actually, right? So if you notice here, I am basically declaring Q, which is my output. All the outputs that you see over here, Q7, Q6, Q5, Q4, Q3, I am essentially declaring them as wire here. Okay, now I need to instantiate the D flip-flop, which I showed you earlier. I need to instantiate that 8 times 57 to 64. I started off, you need to make sure the set of arguments that goes inside, they need to follow the same sequence as you have over here in the main file, which is clock reset, load, input and output, input D and the output, clock reset, load, input D and Q. So if you look over here, when I'm instantiating, I have my D flip-flop. You need to make sure this exactly matches how it appears over here. Follow it up by an instantiator name. This could be anything. I went with D0. Bracket open. Now I'm following the same sequence. Clock, reset, my button debounce. This is the load button, and because I had instantiated my load button with the debounce module, so the output that comes out, this is the debounce. This is the single pulse output, which is button debounce. So that comes over here. Follow it up by Q1. Why it's Q1? This is D flip-flop D0. So if you go back here, D0, what is the input here to D0? Well, the input is Q1. So I'm going to have Q1 here. Correct? What comes out? Well, what comes out is Q0 from this flip-flop. So here I have Q0. Similarly, if you look at D flip-flop D1, clock, reset, button debounce is gonna be same for all. The only thing that changes is the fourth and the fifth argument, right? If you look at D1, what is the input to the D1 and what is the output? Well, input to D1 right here is Q2, output is Q1. Input is Q2, output is Q1. So on, you're gonna follow this block diagram right here. I want to go to the last flip-flop, which is, if you notice here, the input is D, and D is coming from exclusive ORing with Q7, Q5, Q4, Q3. What comes out is Q7. Okay, let's go there. Input, which is input D, is exclusive NORing with Q7, Q5, Q4, Q3. So I just left an expression over there. Yes, you can do that. Comma, output is Q7. So let's do that. And then this Q, basically, the values for the Q will be updated every time the clock arrives. And therefore, there will be a new set of values when a load button is pressed at Q7, Q6, all the way to Q0. And those values are then fed into this binary to BCD module. This is Q, this Q right here. And that takes the input and then does its magic. Again, I don't want to go through this because otherwise it's going to be a long video, and I've already covered this in one of my previous videos. Here's the link for it. I'll leave the link in the description as well. So let's just quickly run the implementation. Select your top module. Oh, by the way, there is a constant file as well. If you look at the constant file, it's pretty simple. You got the clock here, you got the reset button and the load button, and then you got the 7 segments, and then you got the 4 enables, right? You will also find the constant file in the description as well. Let's choose your top module, run implementation. It should take a couple of minutes. Bitstream is complete. At this time, you want to make sure that your FPGA board is connected. Hit open target. Actually, mine is already connected, so I can just go and click on program device, select my family, my target. Your bit file should automatically be up there. Hit program, and there you go. Boom, you should be able to see the implementation of your design on the board. If you are curious, you want to see your schematic, go to RTL analysis, click schematic, hit OK over here, and it should automatically generate your RTL schematic, something that you can use for your demo during your final project and would make a nice presentation. Here is your schematic right here. You can click on these 4 arrows to center it, maximize the window, and zoom in if you like. You can also right click and save it as a PDF file if you wish. Hit OK and it will generate one. I already have one, so I can just cancel it. I hope you enjoyed this video, and if you find this useful, consider subscribing to the channel. Have a wonderful day and stay safe. Bye. Notice this is my reset button, so if I press the reset button, everything goes back to 0. If this is my load button, anytime I press this button, logic changes. Okay, I'm gonna press the button several times, and you will notice that none of the number will get repeated until I have gone through this 255 times, which is the maximum number of random numbers it can generate. And that is all because thanks to those steps, that exclusive NOR logic that we applied.